In the summer of 1987, General Motors was about to abandon a $2.3 billion engine project that had consumed 5 years of development and the careers of dozens of engineers. The revolutionary ceramic engine that was supposed to change the automotive industry forever lay broken in pieces across the factory floor. Senior executives had already drafted the cancellation memo. The media was preparing obituaries for what they called the biggest automotive failure since the Edsel. But in a dimly lit corner of the Pontiac, Michigan facility, something extraordinary was about to happen. Maria Santos, the 19-year-old daughter of night janitor Eduardo Santos, was about to prove that sometimes the most brilliant solutions come from the most unexpected places. She had never set foot inside an engineering classroom, never held a college degree, and never even owned a car. Yet in 3 weeks, she would solve a problem that had stumped teams of PhD engineers and save an engine that would eventually power millions of vehicles worldwide. This is the true story of how a young woman with nothing but curiosity, determination, and a different way of seeing the world turned automotive history upside down. It's a story about the courage to speak up when everyone else has given up, the power of fresh perspective over formal education, and how one person's refusal to accept impossible can change everything. What Maria discovered that summer didn't just save an engine. It revolutionized how we think about innovation, problem solving, and who gets to be called an expert. Her breakthrough would eventually lead to patents worth hundreds of millions of dollars, transform manufacturing processes across multiple industries, and prove that genius doesn't always come with a diploma. The experts said it couldn't be done. The data said it was impossible. The math said it would never work. They were all wrong. This is the story of how they found out. The fluorescent lights hummed overhead as Dr. Richard Pemberton stared at the latest test results spread across his desk. After 32 years at General Motors, he had seen plenty of engineering challenges, but nothing quite like this. The papers before him told a story of failure so complete, so devastating, that even he was beginning to doubt whether the project could be saved. The Advanced Ceramic Engine program had started with such promise back in 1982. The idea was revolutionary. Replace traditional metal engine components with advanced ceramic materials that could withstand temperatures exceeding 2,000 degrees Fahrenheit. Such an engine would be lighter, more fuel-efficient, and dramatically more durable than anything ever produced. It was exactly the kind of breakthrough American automakers needed to compete with the rising tide of Japanese imports that were capturing market share with their superior fuel economy. Pemberton remembered the excitement in the boardroom when the project was approved. CEO Roger Smith himself had championed the initiative, calling it the engine of the future. The company committed unprecedented resources, a dedicated 200,000 square foot facility in Pontiac, Michigan, a team of 150 engineers and technicians, and a budget that would eventually swell to $2.3 billion. The automotive press hailed it as Detroit's moonshot, comparing it to the space program in its ambition and potential impact. But 5 years later, that moonshot was crashing back to Earth. The fundamental challenge was thermal shock. Ceramic materials, while incredibly heat-resistant, were also brittle. When subjected to the rapid temperature changes of a running engine, they would crack and shatter. The engineering team had tried everything: different ceramic compositions, various manufacturing techniques, sophisticated coating systems. They had consulted with experts from universities across the country, brought in specialists from aerospace companies that worked with ceramics in jet engines, even partnered with Japanese firms that were pursuing similar research. Nothing worked. The latest round of tests had been particularly disheartening. Prototype engines that ran perfectly for hours in carefully controlled laboratory conditions would fail within minutes when subjected to real-world driving scenarios. The ceramic cylinder heads would develop hairline fractures that grew into complete failures. Pistons would chip and break apart. Valve components would simply disintegrate under stress. Pemberton's team had documented every failure meticulously. They had high-speed cameras that captured the exact moment when ceramic components failed. They had computer models that predicted stress patterns down to the molecular level. They had temperature sensors that monitored thermal gradients with incredible precision. The data was overwhelming, and it all pointed to the same conclusion. Ceramic engines, while theoretically superior, were practically impossible with current technology. The pressure from above was mounting. The automotive industry was facing one of its worst downturns since the Great Depression. Japanese manufacturers were not just competing on fuel economy anymore, they were also outpacing Detroit in quality and reliability. GM was hemorrhaging market share and desperately needed wins. The ceramic engine project, instead of being that win, was becoming a very expensive albatross. Martha Davidson, the project's chief financial officer, had been particularly blunt in the latest management review. The project was already $800 million over budget, with no clear timeline for success. Market research suggested that even if they solved the technical problems, the engine would be too expensive for mass production. Competitors were making incremental improvements to traditional engines that were achieving much of the fuel economy gains the ceramic engine promised, without the massive development costs. But it wasn't just the financial pressure that weighed on Pemberton, it was the human cost. Several promising young engineers had seen their careers stalled by association with the project. Dr. Jennifer Liu, one of the brightest materials scientists he had ever worked with, had requested a transfer to the conventional engine division after her ceramic valve design suffered its 14th consecutive failure. Tom Morrison, a veteran powertrain engineer, had taken early retirement rather than continue what he called beating our heads against the laws of physics. The facility itself had become a symbol of dashed hopes. What had once buzzed with the energy of innovation now felt more like a museum of failure. Workstations that had been occupied around the clock in the early years now sat empty. The prototype engines, once displayed proudly for visiting executives, were now stored in climate-controlled rooms, where they served as expensive reminders of what hadn't worked. Pemberton walked through the facility that Tuesday morning, observing the handful of team members who remained. In the materials lab, Dr. Bran, Hassan al-Rashid, was still running thermal cycling tests on ceramic composites, his data sheets filled with temperature curves that all ended the same way: catastrophic failure. In the machining center, precision equipment worth millions of dollars sat idle because there was no point in manufacturing components that would inevitably break. The most painful part was the wasted potential. The theoretical advantages of ceramic engines were undeniable. Computer simulations showed they could achieve fuel economy improvements of 3 to 40% over conventional engines. They would last longer, require less maintenance, and produce fewer emissions. For a company and an industry struggling to adapt to changing consumer demands and tightening environmental regulations, such an engine could be transformational. But theoretical advantages meant nothing if the engines couldn't survive real-world conditions. And after 5 years and hundreds of prototypes, Pemberton's team was no closer to solving the fundamental thermal shock problem than they had been at the beginning. The morning of July 15, 1987, brought the news that everyone had been expecting but hoping to avoid. Pemberton was called to a meeting with senior management where the future of the project would be decided. The conference room on the 18th floor of the Renaissance Center overlooked the Detroit River, but the view felt more ominous than inspiring. Present were the usual suspects: Martha Davidson with her spreadsheets and cost projections, Vice President of Engineering James Patterson with his timeline charts, and Director of Advanced Projects Sarah Chen with her competitive analysis reports. But also present was someone Pemberton hadn't expected: Robert Hendricks from Corporate Strategy, the man responsible for deciding which projects lived and which died. The presentation was methodical and devastating. Davidson walked through the financials, showing how the project had consumed resources that could have funded multiple smaller initiatives. Patterson displayed engineering milestones that had been missed repeatedly, with failure rates that showed no meaningful improvement over time. Chen presented market analysis suggesting that competitors were achieving comparable results through evolutionary improvements rather than revolutionary breakthroughs. When it was Pemberton's turn to speak, he found himself in the uncomfortable position of defending a project he was no longer sure could be defended. He talked about the breakthroughs that were always just around the corner, about new materials that showed promise in preliminary testing, about manufacturing techniques that might solve the thermal shock problem. But even to his own ears, the words sounded hollow. The questions that followed were pointed and fair. How much more money would the project require? How much more time? What was the probability of success? Pemberton found himself giving answers that sounded like excuses. More funding? Yes. More time? Certainly. Probability of success? He couldn't honestly say it was better than 5-0. 5-0. The meeting ended without a formal decision, but the writing was on the wall. Hendricks spoke with the cold precision of someone who had made these decisions before. The project had 3 weeks to demonstrate significant progress or face cancellation. Given the pattern of the past 5 years, that was effectively a death sentence. Pemberton returned to his office feeling older than his 59 years. Through his window, he could see the Pontiac facility, where his team continued their work, unaware that they were likely living through the final chapter of their project. He thought about all the brilliant minds that had contributed to the effort, all the innovative solutions that had been attempted, all the dreams that had been invested in the ceramic engine concept. Outside his office, the broader facility was already showing signs of the project's uncertain future. Support staff had been reassigned to other projects. Equipment leases were not being renewed. The enthusiastic reports that had once filled management briefings had been replaced by dry technical summaries that documented problems without offering solutions. The irony was not lost on Pemberton. In trying to create the engine of the future, they had perhaps spent too much time in laboratories and computer simulations, too little time thinking about the fundamental challenge from a different perspective. They had approached the problem as a materials science challenge, as an engineering optimization problem, as a manufacturing puzzle. But perhaps they had missed something more basic, more human. As the day ended and the facility began to empty, Pemberton remained at his desk, staring at the test results that told the same story they had been telling for months. The ceramic engine project, barring a miracle, was finished. The experts had been defeated by a problem that seemed to have no solution. But sometimes miracles come from the most unexpected places, and sometimes the most brilliant solutions are hiding in plain sight, waiting for someone who sees the world just a little differently to notice them. That someone was already in the building, though Dr. Gerb. Richard Pemberton didn't know it yet. She was mopping floors 3 stories below, listening to the conversations of departing engineers and thinking about problems in ways that PhD dissertations had never taught anyone to consider. The countdown to cancellation had begun, but the real story was just beginning. Eduardo Santos had been cleaning floors at the General Motors facility for 8 years, but he had never seen the engineers look quite this defeated. As he pushed his cart through the ceramic engine laboratory at 11:30 p.m., he noticed the way they had left their workstations. Papers scattered, coffee cups abandoned half full, computer screens still glowing with data that told stories of failure. Eduardo took pride in his work. While others might see him as just another member of the cleaning crew, he understood that his job was essential. These brilliant minds needed clean, organized spaces to think clearly. He made sure every surface was spotless, every piece of equipment properly maintained, every wastebasket emptied. In his 8 years at the facility, he had developed an appreciation for the complex work happening around him, even if he didn't fully understand the technical details. What Eduardo did understand was disappointment. He had seen it before in other projects that had been cancelled over the years. He recognized the signs, the gradual reduction in staff, the equipment that sat unused, the conversations that stopped when he entered a room. The ceramic engine project was in trouble, and everyone knew it. But Eduardo also understood something else that perhaps the engineers had forgotten: the value of seeing problems from a completely different angle. Growing up in rural Mexico, he had learned to solve problems with creativity rather than expensive equipment. When the old tractor on his father's farm broke down, they couldn't call a certified technician or order replacement parts from a catalog. They had to figure out solutions using whatever materials were available, often approaching problems in ways that would horrify engineering textbooks but somehow worked. It was this practical problem-solving mindset that Eduardo had tried to instill in his daughter Maria. At 19, she was everything he had dreamed she could become: intelligent, curious, hard-working, and accepted to the University of Michigan's engineering program starting in the fall. She had earned a summer job in the facility's administrative offices, filing reports and managing correspondence for the ceramic engine project. It was meant to be temporary work to save money for college, but Eduardo knew she was absorbing far more than anyone realized. Maria Santos had always been different. Even as a child, she approached problems in ways that surprised adults. When other kids couldn't reach something on a high shelf, they would ask for help or drag over a chair. Maria would study the situation, consider all available resources, and often come up with solutions that were both more creative and more effective. She might use a combination of books, boxes, and careful positioning to create a stable platform, or she might find an entirely different way to accomplish the same goal without needing to reach the high shelf at all. This unconventional thinking had served her well academically. While her classmates memorized formulas and followed textbook procedures, Maria developed an intuitive understanding of why those formulas worked and when they might not apply. Her physics teacher had once commented that she had a natural engineer's mind, someone who could see the fundamental principles behind complex systems. Now, working in the ceramic engine facility, Maria was witnessing those fundamental principles being pushed to their limits. Through her administrative duties, she had access to technical reports, test results, and design specifications. She read everything she could get her hands on, not because it was required for her job, but because she was genuinely fascinated by the challenge the engineering team was trying to solve. The thermal shock problem made sense to her in a way that surprised even herself. Ceramics were like many things in nature, incredibly strong under certain conditions, but vulnerable to rapid changes. She thought about how glass could be made incredibly strong through careful heat treatment, but would shatter if subjected to sudden temperature changes. She remembered watching her grandmother cook, how certain clay pots had to be heated gradually or they would crack. But what intrigued Maria most was something she observed during her father's work shifts. Eduardo had gotten permission for her to occasionally help with cleaning duties during particularly busy periods, and she noticed something the engineers seemed to have missed: the patterns of how heat moved through the facility itself. The ceramic engine laboratory was a precisely controlled environment. Temperature and humidity were monitored constantly. Air circulation was carefully managed to prevent contamination of sensitive materials. But Maria noticed that despite all this control, there were still natural variations in how heat moved through different areas of the lab. Some workstations were consistently slightly warmer than others, even though the environmental controls suggested they should all be identical. One evening in mid-July, as the 3-week deadline approached, Maria was helping her father clean the main laboratory when she overheard a conversation between Dr. Pemberton and Dr. Rui al-Rashid. They were discussing the latest round of failed tests, specifically how ceramic components seem to fail in predictable patterns related to heat gradients. "It's as if the material can't adapt fast enough," Dr. al-Rashid was saying. "The theoretical heat transfer coefficient suggests it should work, but in practice we're getting localized stress concentrations that lead to crack propagation." Dr. Pemberton nodded wearily. "We've tried preheating, gradual temperature ramping, even variable thermal cycling. Nothing seems to make a difference. The ceramics just can't handle the shock of going from ambient temperature to operating temperature quickly enough for practical applications." As they left the laboratory, Maria found herself thinking about their conversation. She understood the basic problem. Ceramic materials could handle high temperatures just fine, but they couldn't handle rapid temperature changes. The solution seemed obvious to the engineers: control the temperature changes more carefully, but that approach wasn't working. That night, Maria couldn't sleep. She kept thinking about the thermal shock problem, but also about something else she had observed. During her cleaning duties, she had noticed that some of the failed ceramic components showed very different crack patterns depending on where they had been tested. Components tested in one area of the lab showed radial cracking, while those tested in another area showed more linear failure patterns. She had initially dismissed this observation as unimportant. After all, she wasn't an engineer, and the sophisticated testing equipment surely accounted for any environmental variations. But the more she thought about it, the more convinced she became that this pattern was significant. The engineers were approaching the problem as if all thermal shock was the same. But what if it wasn't? What if the specific way heat moved through ceramic materials was more complex than their models suggested? The next evening, Maria arrived at the facility early and spent time in the laboratory before the cleaning shift began. She had her father's permission to be there, and she used the time to carefully examine the failed ceramic components. What she found confirmed her suspicion. The failure patterns were not random. Components that failed in different areas of the lab showed consistently different crack characteristics. More importantly, she began to understand why. The laboratory's environmental controls maintained overall temperature consistency, but they couldn't eliminate tiny variations in airflow, humidity, and thermal radiation from different equipment. These small variations created microclimates within the laboratory that affected how heat moved through ceramic materials during testing. But Maria realized something even more significant. These microclimates weren't just affecting the test results, they might actually be the key to solving the thermal shock problem. Instead of trying to eliminate thermal variations, what if they could harness them? What if controlled thermal gradients could actually help ceramic materials adapt to temperature changes more gradually? The idea was counterintuitive. Every engineering approach had focused on creating uniform thermal conditions. But Maria's observation suggested that carefully designed non-uniform conditions might actually be better. It was like the difference between jumping into a hot bath versus gradually increasing the water temperature, the same end result, but a completely different experience for the material. She spent the following days developing her theory, reading through technical literature in the facility's library during her lunch breaks, and carefully observing the testing procedures when she could do so without interfering. The more she learned, the more convinced she became that the engineering team was solving the right problem with the wrong approach. The breakthrough came when she realized that nature had already solved this exact problem. Tree bark, animal shells, even human bone, all were materials that had to handle thermal shock in varying conditions. But they didn't do it through uniform material properties. Instead, they used gradient structures that transitioned gradually from one type of material behavior to another. What if ceramic engine components could be designed the same way? Instead of uniform ceramic throughout, what if they used gradient materials that transition from metal to ceramic? The metal portions could handle rapid temperature changes, while the ceramic portions provided high-temperature performance. The gradient between them would eliminate the sharp interface that created stress concentrations. It was an elegant solution, but Maria knew she faced a significant challenge. She was a 19-year-old college student with no formal engineering credentials, working in an administrative capacity on a project that had stymied some of the most brilliant minds in the automotive industry. How could she possibly convince anyone to take her seriously? The answer came from an unexpected source: her father. Eduardo had been watching his daughter's growing fascination with the ceramic engine problem, and he had seen the late nights she spent reading technical papers and the careful observations she made during her time in the laboratory. He might not understand the technical details, but he understood his daughter's mind. When Maria explained her theory to him, Eduardo made a decision that would change everything. "Mija," he said, "sometimes the most important thing is not whether people think you're qualified to have an idea. Sometimes the most important thing is whether the idea is right, and if you believe this idea is right, then you have to find a way to share it." Eduardo had been in the facility long enough to understand its politics and personalities. He knew that Dr. Pemberton was under enormous pressure, that the project was days away from cancellation, and that conventional approaches had failed repeatedly. He also knew that Dr. Kapkin said Pemberton was the kind of person who would listen to a good idea regardless of where it came from. The plan Eduardo suggested was simple but required courage. Maria would request a brief meeting with Dr. Pemberton to present her observations and theory. She would be honest about her background and qualifications, but she would focus on the technical merit of her idea. If she could present her case clearly and convincingly, then maybe, just maybe, it might be enough to give the project new direction. As Maria prepared for what might be the most important conversation of her young life, neither she nor her father realized they were about to trigger events that would not only save the ceramic engine project, but fundamentally change how the automotive industry thought about material science and innovation. The night shift had revealed more than anyone expected, and the most important discovery was still to come. Dr. Richard Pemberton was reviewing the final shutdown procedures when his secretary knocked on his office door. It was Thursday morning, July 16, 1987, and he had exactly 1 week before the official project cancellation announcement. The last few team members were already packing their personal belongings, and equipment vendors had been notified to prepare for acid removal. "Dr. Pemberton, there's someone here who says she has information about the ceramic engine project," his secretary announced. "A young woman from the administrative staff. She's quite insistent that she needs to speak with you." Pemberton looked up from his desk, where failure reports were stacked in neat piles that represented 5 years of unsuccessful research. Under normal circumstances, he might have politely declined such a meeting. He had already spent countless hours listening to suggestions from well-meaning colleagues, outside consultants, and even a few inventors who claimed to have revolutionary solutions. None had led anywhere productive, but these were not normal circumstances. In 1 week, his career's most ambitious project would officially end in failure. He had already begun drafting farewell letters to team members and preparing his final report for corporate management. What could it hurt to listen to one more perspective, even from someone who presumably had no engineering background? "Send her in," he said, curious despite his exhaustion. Maria Santos entered the office wearing the simple business attire appropriate for her administrative role, carrying a manila folder that contained carefully handwritten notes and sketches. At 19, she looked even younger than her age, and Pemberton found himself wondering what could have motivated someone in her position to request this meeting. "Dr. Pemberton, thank you for seeing me," Maria began, her voice steady despite her nervousness. "I know you're very busy, especially with the project deadline approaching. I'm Maria Santos. I work in the administrative office processing reports for the ceramic engine program. I realize I don't have engineering credentials, but I've been observing something that I think might be important for your project." Pemberton gestured for her to sit down, intrigued by her directness. In his experience, people without technical backgrounds who offered engineering advice usually began with lengthy disclaimers about their lack of qualifications. Maria's approach was refreshingly straightforward. "What kind of observations?" he asked. Maria opened her folder and pulled out her first sheet of notes. "Dr. Pemberton, I've been reading the technical reports that come through our office, and I've also been able to observe some of the testing procedures during my evening duties. I've noticed patterns in the failure modes that don't seem to match the current design assumptions." She spread out hand-drawn diagrams that showed the ceramic engine laboratory layout with different areas marked and annotated. The failed ceramic components showed different crack patterns depending on where they were tested in the laboratory. Components tested in workstation area A consistently show radial cracking, while those tested in area C show more linear failure patterns. Components from area B showed intermediate characteristics. Pemberton studied the diagrams, his interest growing. He had been so focused on the material properties and thermal cycling parameters that he had never considered whether the testing environment itself might introduce variables. That's actually quite observant. Have you discussed this with any of the testing technicians?
No, sir, Maria replied.
I wasn't sure if it was significant until I started thinking about why it might be happening. I believe the laboratory has microclimates that affect thermal transfer in ways that aren't accounted for in the current testing protocols. She pulled out another sheet that showed airflow patterns she had observed and mapped. The environmental controls maintain overall temperature consistency, but there are still small variations in air circulation, thermal radiation from different equipment, and even humidity that create slightly different conditions in different parts of the lab. Pemberton found himself leaning forward, his attention now completely focused on what Maria was saying. In 32 years of engineering, he had learned to recognize when someone was onto something significant. The patterns she had identified were subtle, but they were real, and they suggested that the testing protocols might indeed be missing important variables. But here's what I think is really important, Maria continued, her confidence building. These microclimates aren't just affecting test results. They might actually be showing us how to solve the thermal shock problem. Instead of trying to eliminate thermal variations, what if we could use controlled thermal gradients to help ceramic materials adapt to temperature changes more gradually? She turned to a page that showed her analysis of natural materials that handled thermal shock successfully. I've been reading about how biological materials solve similar problems. Tree bark doesn't crack when temperature changes rapidly, because it has gradient properties. It transitions gradually from one type of material behavior to another. Animal shells work the same way. Even human bone uses gradient structures to handle stress. Pemberton was now studying her diagrams with the intensity he usually reserved for peer-reviewed research papers. What Maria was describing represented a fundamentally different approach to the thermal shock problem. Instead of trying to make uniform ceramics more resistant to temperature change, she was suggesting a gradient approach that would eliminate the sharp material property transitions that created stress concentrations. This is fascinating thinking, he admitted. But implementing gradient materials in ceramic engine components would require completely redesigning our manufacturing approach. We're talking about creating components that transition from metal properties to ceramic properties in a controlled way. That's not just a material science challenge, it's also a precision manufacturing challenge. Yes, sir, Maria agreed. But I think the current manufacturing capabilities might be closer to supporting this approach than it initially appears. The plasma spraying techniques your team has been developing for ceramic coatings could potentially be adapted to create gradient layers. Instead of applying uniform ceramic coatings to metal substrates, you could apply multiple layers with gradually changing compositions. Pemberton paused, his mind racing through the implications. Maria was right that their existing plasma spraying equipment could theoretically support gradient layering approaches. The fundamental challenge would be controlling the composition and thickness of each layer with sufficient precision to create smooth property transitions. There's another aspect I wanted to mention, Maria continued. I noticed that some of the most successful ceramic components in your test results came from batches that had what the reports classified as manufacturing irregularities. When I looked at those irregularities more closely, many of them were actually unintentional gradient effects, places where the ceramic composition or density varied slightly. She showed him data points she had extracted from various test reports and reorganized to highlight this pattern. Components with these unintentional gradients lasted significantly longer before failure, but the variations were dismissed as quality control issues rather than being studied as potential improvements. This observation hit Pemberton like a thunderbolt. He remembered several instances where components had performed unexpectedly well, only to be discounted because they didn't match the intended specifications exactly. The quality control team had indeed classified such variations as manufacturing defects to be eliminated rather than studied and potentially replicated. Maria, this is remarkable analysis, Pemberton said, his excitement building. You're essentially proposing that we've been solving the wrong problem. Instead of trying to create perfect uniform ceramics, we should be trying to create controlled, imperfect gradients. Exactly, Maria replied. And I think the path to implementation might be simpler than starting from scratch. Some of your existing components could be modified to test the gradient approach. The ceramic pistons, for example, could be redesigned with metal cores and ceramic outer layers, with carefully controlled transition zones between them. Pemberton stood up and began pacing, as he always did when his mind was working through complex problems. Maria's insight represented a paradigm shift that could potentially rescue the project, but it would require convincing management to extend the timeline and modify the approach when they were already convinced that the project was a failure. Maria, I have to ask, how did you develop this analysis? You mentioned reading technical reports, but the level of understanding you're demonstrating goes well beyond what most people could extract from technical literature. Maria smiled for the first time during the meeting. Dr. Pemberton, I'm starting engineering school at the University of Michigan in the fall. But more importantly, I grew up watching my father solve problems in creative ways when conventional approaches didn't work. I learned to look at problems from multiple angles and to pay attention to patterns that might not be obvious at first. I also have to be honest, she continued. I've been fascinated by this project since I started working here. I've spent most of my free time reading everything I could find about ceramic materials and thermal shock. I might not have formal credentials yet, but I've put in the time to understand the fundamentals. Pemberton returned to his desk and looked at the shutdown timeline that had been governing his recent decisions. Maria's insights were compelling enough to warrant serious consideration, but implementing her suggestions would require resources, time, and management support that might no longer be available. Maria, what you're proposing could potentially save this project. But I need to be honest with you about our situation. We have less than 1 week before the project faces cancellation. Even if your approach is correct, proving it would require extensive testing and development that could take months. I understand, Maria replied. But could we design a quick proof of concept test? Something simple enough to implement with existing equipment and materials, but comprehensive enough to demonstrate whether the gradient approach has merit. Pemberton considered this carefully. A properly designed proof of concept could potentially be completed within the remaining timeframe, especially if they focused on modifying existing components rather than creating entirely new designs. If Maria's theory was correct, even a crude implementation of the gradient approach should show measurable improvement over current results. You know what, Maria? Let's try it. I can't promise that management will extend the project deadline, but I can promise that we'll give your approach a fair test. If you're willing to work with our team for the next few days, we'll see if we can prove your theory. As Maria left his office that morning, Pemberton found himself feeling something he hadn't experienced in months. Genuine optimism. After years of approaching the thermal shock problem from every conceivable engineering angle, a 19-year-old administrative worker had potentially identified the fundamental flaw in their approach. But optimism alone wouldn't save the project. They now had 6 days to prove that gradient materials could succeed where uniform ceramics had failed. 6 days to design, manufacture, and test components based on an entirely new paradigm. 6 days to turn Maria's insights into results that could convince skeptical executives to continue funding the most expensive automotive research project in company history. The race against time had begun, but for the first time in years, they were running toward a solution that might actually work. Within hours of Maria's meeting with Dr. Bate, Pemberton, the ceramic engine laboratory, was buzzing with an energy that hadn't been felt in months. The skeleton crew that remained on the project found themselves pulled into an urgent effort to test a completely new approach to thermal shock resistance, with only 6 days to prove it could work. Dr. Pemberton had made a decision that surprised even himself. Instead of conducting the test quietly with minimal resources, he was committing the project's remaining budget and personnel to give Maria's gradient theory the most thorough evaluation possible in the limited time available. If the approach showed promise, he wanted results compelling enough to demand management attention. If it failed, at least they would go down fighting. Dr. Hassan al-Rashid was the first senior engineer to fully understand what Maria was proposing. When Pemberton explained the gradient materials concept, al-Rashid initially responded with skepticism. He had spent 3 years trying every conceivable variation of ceramic composition and manufacturing technique. The idea that a fundamental change in approach, suggested by someone without formal engineering training, could solve their problem seemed almost insulting to his professional expertise. But as he studied Maria's analysis of the failure patterns and her observations about microclimates in the laboratory, his skepticism began to transform into curiosity. Maria had identified patterns that he had been too close to the problem to notice. Her outsider perspective had allowed her to see the forest, while the engineering team had been focused on individual trees. The mathematics actually support her theory, al-Rashid admitted to Pemberton late Thursday evening. Gradient materials would eliminate the sharp stress discontinuities that cause crack initiation. We've been trying to make ceramic materials behave like metals under thermal shock conditions when we should have been creating hybrid materials that combine the best properties of both. The challenge now was implementation. Creating gradient materials required precise control over material composition at very small scales. The plasma spraying equipment they had been using for ceramic coatings could theoretically be adapted for this purpose, but it would require completely new process parameters and quality control methods. Dr. Jennifer Liu, who had requested transfer from the project just weeks earlier, heard about the new approach and asked to be involved in the testing. Her expertise in materials characterization would be essential for analyzing whether the gradient structures were actually being created as intended. If we're going to do this, we need to do it right, Liu told the assembled team Friday morning. We can't just spray different materials and hope they create the proper gradients. We need real-time monitoring of composition, temperature, and layer thickness. We need to understand exactly what we're creating. The team decided to focus their proof-of-concept effort on ceramic valve components, which had been one of the most persistent failure points in previous testing. Valves were subject to extreme thermal cycling as hot combustion gases flowed past them, and the sharp temperature transitions had consistently caused cracking in uniform ceramic designs. Maria worked alongside the engineers, contributing observations and suggestions while learning firsthand about manufacturing processes she had only read about in technical literature. Her role evolved from consultant to active team member as her insights continued to refine their approach. The first challenge was determining the optimal gradient profile. How many layers should the transition include? How should the composition change from the metal core to the ceramic surface? Should the transition be linear or follow some other mathematical function? Maria suggested they look to natural examples for guidance. Tree bark doesn't transition from wood to protective outer layer in a linear way, she observed. The changes are more gradual in some areas and more rapid in others, depending on the specific stresses each layer needs to handle. This led to a breakthrough in their design approach. Instead of creating uniform gradients, they would create functional gradients, transition zones designed specifically to handle the stress patterns that their computer models predicted for each part of the valve. The manufacturing process required 3 days of intensive trial and error. The plasma spraying equipment had to be recalibrated for each layer of the gradient, with precise control over powder feed rates, plasma temperature, and spray velocity. Each valve component required multiple passes to build up the gradient structure, with cooling periods between layers to prevent thermal damage. Maria proved invaluable during the manufacturing phase, not because of her technical knowledge, but because of her ability to spot patterns and anomalies. She noticed when the plasma spray patterns weren't consistent, when the cooling cycles needed adjustment, and when the finished component showed visual cues that suggested problems with the gradient structure. By Monday morning, they had produced 12 valve components with different gradient profiles for testing. The components looked different from traditional ceramic valves. Their surfaces showed subtle color variations that indicated the changing material composition from core to surface. The testing protocol was designed to be as realistic as possible given their time constraints. Instead of the gradual thermal cycling that had been used in previous tests, they subjected the valves to rapid temperature changes that simulated actual engine operating conditions. Thermocouples monitored temperatures at multiple points on each valve, while high-speed cameras captured any crack initiation or propagation. The first test began at 9 a.m. on Monday. Within minutes, it was clear that something was different. The gradient valves were handling thermal shock conditions that had caused immediate failure in uniform ceramic components. Temperature measurements showed that the gradient structure was indeed distributing thermal stress more effectively across the component, but the real breakthrough came during the third hour of testing. Dr. Al-Rashid was monitoring the data when he noticed something unprecedented. The gradient valves were not just surviving the thermal shock, they were actually getting better at handling it. The repeated thermal cycling was causing the gradient layers to settle into optimal stress distribution patterns, essentially self-optimizing their thermal shock resistance. This is extraordinary, Al-Rashid announced to the team. We're seeing adaptation behavior that we never observed with uniform materials. The gradient structure is learning to handle thermal stress more effectively over time. By Tuesday afternoon, the gradient valves had survived thermal cycling tests that represented weeks of normal engine operation. More importantly, detailed analysis showed no signs of crack initiation or other failure modes that had plagued previous designs. The stress distribution patterns were exactly what Maria's theory had predicted. Dr. Collins, Pemberton called an emergency meeting with the team to review their results and prepare for the management presentation that could determine the project's future. The data was compelling, but they needed to present it in a way that demonstrated both the technical merit of the approach and its commercial viability. "We're not just showing that gradient materials work," Pemberton explained. "We're showing that Maria's insight has fundamentally changed how we think about ceramic engine components. This isn't an incremental improvement, it's a paradigm shift that could apply to multiple engine systems." The team worked through Tuesday night preparing their presentation. Maria found herself in the surreal position of helping to prepare slides that would present her theory to the same executives who had been ready to cancel the project. Her role in the discovery was prominently featured, along with detailed explanations of how her observations had led to the breakthrough. Wednesday morning brought the moment of truth. The conference room was packed with executives, including Robert Hendricks from Corporate Strategy, who had effectively issued the cancellation ultimatum just 1 week earlier. Also present were representatives from manufacturing, quality control, and cost analysis, all the stakeholders who would need to support the project's continuation. Dr. Pemberton began the presentation by acknowledging the project's previous failures and the circumstances that had led to the cancellation deadline. But then he shifted to describing the new approach, with Maria presenting her own observations and analysis that had led to the gradient materials concept. The response was initially skeptical. How could a 19-year-old administrative worker have identified a solution that had eluded teams of experienced engineers? Was this just another promising idea that would ultimately fail under rigorous testing? But the test results spoke for themselves. Video footage showed gradient valve components surviving thermal conditions that had destroyed traditional ceramic designs within minutes. Data charts demonstrated stress distribution patterns that eliminated the failure modes that had plagued the project for 5 years. The presentation concluded with manufacturing analysis showing that gradient materials could actually be produced more cost-effectively than the ultra-pure ceramic components they had been attempting to create. The plasma spraying process was already proven technology, and the gradient approach was more tolerant of minor variations than the precision uniformity previously required. Robert Hendricks asked the question that everyone was thinking: if this approach is so promising, why didn't we discover it sooner? What does this tell us about our engineering processes? Dr. Pemberton answered honestly, Maria brought a perspective that we had lost over 5 years of focused technical development. She saw patterns that we had dismissed as irrelevant because they didn't fit our preconceived notions about how ceramic materials should behave. Sometimes breakthrough innovation requires stepping outside established expertise and looking at problems from completely different angles. The meeting ended with conditional approval for project continuation. Management would provide 6 months of additional funding to fully develop the gradient materials approach, with the understanding that commercial viability would need to be demonstrated within that timeframe.
As the executives filed out of the conference room, Maria found herself surrounded by engineers and managers who wanted to understand how she had developed her insights.
For someone who had entered the building as a temporary administrative worker, the transformation was overwhelming. But the real transformation was just beginning. The gradient materials approach wouldn't just save the ceramic engine project, it would revolutionize how the automotive industry thought about materials science and innovation, with implications that would extend far beyond engines into multiple manufacturing sectors. Maria Santos had proven that sometimes the most valuable expertise comes not from years of formal training, but from the courage to see familiar problems in unfamiliar ways. 3 years after Maria Santos walked into Dr. Pemberton's office with her manila folder full of observations, the automotive industry was in the midst of a materials science revolution. The gradient ceramic engine technology had not only succeeded beyond anyone's original expectations, but it had spawned an entire new field of engineered materials with applications far beyond automotive use. The first production vehicles, equipped with gradient ceramic engines, rolled off assembly lines in Detroit in the spring of 1990. The initial production run was limited to 10,000 vehicles, carefully monitored to ensure that real-world performance matched laboratory results. The engines delivered fuel economy improvements of 35%, exactly matching the original theoretical predictions, while exceeding durability targets by significant margins. Maria Santos, now 22 and a senior engineering student at the University of Michigan, had become something of a celebrity in automotive circles. Her discovery had been featured in engineering journals, automotive magazines, and business publications. She held patents on several aspects of the gradient materials technology that would eventually generate hundreds of millions of dollars in licensing revenue. But perhaps more importantly, Maria had become a symbol of how innovation could come from unexpected sources. General Motors had established the Santos Innovation Fellowship, a program that encouraged employees at all levels to contribute ideas for technical challenges. The program had already generated dozens of promising concepts, several of which were in development. Dr. Richard Pemberton, now Director of Advanced Materials Research, often reflected on how close they had come to cancelling what would become one of the most successful automotive technologies of the decade. The Gradient Ceramic Engine project had not only survived its near-death experience, it had thrived in ways that surpassed the original vision. The technical success was only part of the story. The gradient materials approach had applications in aerospace, where temperature gradients were even more extreme than in automotive applications. Aircraft engine manufacturers were licensing the technology for turbine blades and combustion chambers. The space program was exploring gradient materials for heat shields and rocket engine components. But the broader impact was cultural. Maria's story had fundamentally changed how engineering organizations thought about innovation and expertise. The assumption that breakthrough insights required advanced degrees and years of experience had been permanently shattered. Companies across multiple industries were implementing programs to tap into the knowledge and perspectives of workers who traditionally hadn't been included in technical development processes. Eduardo Santos watched his daughter's transformation with a mixture of pride and amazement. The young woman who had once helped him clean laboratory floors was now consulting with senior executives on materials science strategy. She had been offered full scholarships to graduate programs at MIT, Stanford, and Caltech, with guaranteed research funding for any project she wanted to pursue. But Maria had chosen a different path. Instead of immediately pursuing graduate school, she was working part-time at GM while finishing her undergraduate degree, focusing on the practical implementation of gradient materials technology. She had discovered that she loved the challenge of turning theoretical concepts into real-world applications. "I want to understand how innovations actually get from laboratories to production lines," Maria explained to Dr. Pikert Pemberton during one of their regular meetings. Too often, great technical ideas fail because nobody thinks about manufacturing feasibility, cost constraints, or market timing. I want to help bridge that gap. The Gradient Ceramic Engine program had indeed faced all those challenges. Scaling from laboratory prototypes to production volumes had required solving hundreds of manufacturing problems that hadn't been apparent in initial testing. Quality control for gradient materials was far more complex than for uniform materials, requiring new testing methods and acceptance criteria. Cost management had been equally challenging. While gradient materials were ultimately less expensive than ultra-pure ceramics, the manufacturing process required significant capital investment in modified plasma spraying equipment. The business case had required careful analysis of production volumes, market acceptance, and competitive positioning. Market timing had been crucial. The Gradient Ceramic Engines launched just as environmental regulations were tightening and consumers were becoming more concerned about fuel economy. The technology arrived at exactly the right moment to meet market needs. Dr. Jennifer Liu, who had returned to lead the materials characterization team, often worked with Maria on understanding how gradient structures behaved under various operating conditions. Their collaboration had led to several innovations in gradient design optimization, including computer modeling techniques that could predict optimal layer compositions for specific applications. Maria has an intuitive understanding of how materials behave that complements our analytical approaches perfectly, Liu observed. She can often predict how a material will perform just by looking at its structure, while our computer models confirm and quantify what she's already figured out. The success of the Gradient Ceramic Engine had also vindicated several other unconventional decisions that Dr. Pemberton had made during the crisis period. The decision to involve someone without formal engineering credentials in technical development had proven that diversity of perspective was just as important as depth of expertise. The decision to commit remaining resources to testing an unproven approach rather than managing a graceful shutdown had demonstrated the value of taking calculated risks. But perhaps most importantly, the project had shown that breakthrough innovation often required abandoning conventional assumptions. The engineering team had spent 5 years trying to make ceramic materials behave like ideal ceramics, when the solution was to make them behave like hybrid materials that combine ceramic and metallic properties. By 1990, gradient materials technology was being applied to applications that the original ceramic engine team had never imagined. Medical device companies were using gradient materials for implants that needed to interface between bone and artificial components. Electronics manufacturers were exploring gradient materials for heat management in computer processors. Even construction companies were investigating gradient concrete compositions for structures subject to extreme temperature variations.
Maria found herself at the center of this expanding application ecosystem.
Her original insights about thermal stress distribution and materials gradients were proving relevant across multiple industries. She was regularly invited to speak at technical conferences, consult with development teams and review research proposals. The financial rewards had been substantial as well. Her patent portfolio related to gradient materials was generating licensing income that would ensure her financial security for life. But more importantly to Maria, the patents were structured to encourage widespread adoption of the technology rather than restricting its use. She had insisted on reasonable licensing terms that would make gradient materials accessible to smaller companies in developing markets. General Motors' investment in the ceramic engine project had also paid off handsomely. The technology provided a significant competitive advantage in fuel economy, reliability, and environmental performance. Market share that had been lost to Japanese manufacturers was being recovered as American automakers demonstrated technological leadership in advanced materials. The broader automotive industry had been forced to respond. Competing manufacturers were developing their own advanced materials programs, leading to an acceleration of innovation across the sector. The gradient materials concept had triggered a wave of research into other hybrid material approaches, functionally graded components, and bio-inspired engineering solutions. Academic institutions had also taken notice. Engineering curricula were being modified to include more emphasis on interdisciplinary thinking, practical problem-solving, and innovation processes. The traditional focus on theoretical analysis was being balanced with courses that emphasized observation, pattern recognition, and creative synthesis. Maria's story had become a case study taught in business schools, engineering programs, and innovation management courses. Her approach demonstrated how breakthrough thinking could emerge from careful observation, willingness to challenge assumptions, and the courage to present ideas despite lacking traditional credentials. As Maria prepared to graduate from the University of Michigan in 1991, she faced choices that would have seemed impossible just 4 years earlier. Research laboratories around the world were competing to recruit her. Technology companies were offering positions that would allow her to lead innovation programs. Graduate schools were providing opportunities to pursue advanced degrees in any field that interested her. But Maria had already decided on her next step. She was joining General Motors as Director of Breakthrough Technologies, a new position created specifically for her. Her mandate was to identify and develop the next generation of revolutionary technologies that could transform automotive manufacturing. The Gradient Materials Project taught me that the most important innovations often come from changing how we think about problems rather than just applying more sophisticated solutions to existing approaches. Maria explained to the university newspaper in her graduation interview, "I want to continue finding those perspective shifts that can unlock new possibilities." Pemberton, who would soon retire as one of the most successful automotive engineers of his generation, often reflected on the lessons learned from the ceramic engine project. The technical achievement was significant, but the human lessons were even more profound. Maria taught us that expertise isn't just about what you know, it's also about how you see. Pemberton wrote in his final project report, "Sometimes the most valuable insights come from people who haven't yet learned what's supposedly impossible." The challenge for any organization is creating environments where those insights can be heard and acted upon. The ceramic engine facility in Pontiac, Michigan had been transformed from a symbol of expensive failure to a showcase of American innovation. Tours of the facility were regularly requested by international delegations, competing manufacturers, and academic researchers who wanted to understand how breakthrough innovation actually happened. But the most meaningful transformation was personal. Eduardo Santos continued his work as a facilities maintenance supervisor, but now he was also consulted on facility design projects and employee innovation programs. His understanding of how physical environments affected creative thinking had proven valuable across multiple GM locations. "I always knew my daughter was special," Eduardo reflected, "but I never imagined that her curiosity and my work cleaning floors would combine to change an entire industry." It shows that important contributions can come from anywhere if organizations are willing to listen. As 1991 ended, gradient ceramic engines were powering vehicles across America, Europe, and Asia. Technology that had nearly been cancelled was generating billions of dollars in revenue and establishing new standards for automotive performance. Patents derived from Maria's original insights were enabling innovations in dozens of other industries, but perhaps the most important legacy was cultural. The story of how a janitor's daughter had saved a failing project by questioning fundamental assumptions had become a symbol of democratic innovation. It demonstrated that, in the right circumstances, breakthrough thinking could emerge from anyone willing to observe carefully, think creatively, and speak up courageously. The revolution that began in a dimly lit laboratory had spread far beyond automotive engineering. It had changed how organizations thought about innovation, expertise, and the sources of transformational ideas. And it all started because a young woman noticed patterns that PhDs had overlooked and had the courage to believe that her observations mattered. The engine was no longer finished. In fact, it was just the beginning.